Welcome everyone. This is my second senior project, and my advisor is Kadri Hoca, which is not here with us. And before starting, I want to thank him for his guidance. Okay, so I will talk about extended topological quantum field theories. My previous senior project was on quantum field theories and topological quantum field theories, and this is the continuation of this project into the extended part. So I will start with a brief introduction. Then I will briefly summarize what we have done in previous semester, TQFT theory, together with its definition, category theory aspects, and the main equivalence result. I will talk about this. And the main part of this project is the extended topological field theories, TFT. I will first begin talking about bicategories and two categories, and I will give homotopy theory as a motivation for bicategories. And then we will define the eTFT formally, and at the end, we will see a similar classification results, this time with the extended. Extended TFTs will be equivalent to the not commutative Frobenius algebras, but separable commutative Frobenius algebras. We will see. Okay, so before starting, this is not a physics talk, so I don't know that parts. So it is fully mathematical approach to TFTs. Okay, so TQFT is a simplified formalization of quantum field theories, and with the help of functor points approach, this is basically what unit implies. We think these theories as functors, and we work in mathematics them as a functor. And they have two main uses. First, for physicists, they are Weber models for quantum field theories. If your model doesn't work on TQFT, there is no hope to work in the real world. And second, for mathematicians, TQFTs are used to produce manifold invariants, which we will see not example, but a motivation. And these two uses create the need for extension. I will talk about the motivation later. Again, our playground is category theory. So extending TQFT means extending category theory. That is why we will be talking about bicategories. Okay, so let's briefly remember categories. A category is a collection of objects together with maps between them, and we have associativity and identity modes for composition. A functor is a mapping between categories, and it sends objects to objects and morphisms to morphisms. And similarly, we have a concept of natural transformation. It is from a functor f to g, and it is compatible with the structure of functors. Okay, so we will mainly deal with monoidal categories, and they are categories with a binary operation, similar to the tensor product. Two examples. You can think the category of sets together with disjoint union, and the identity element in this case is the empty set. If you take union with empty sets, you change nothing. And we have a twist map. Twist map is the disjoint union of two categories. If you switch the order, changes, but not very much. They are canonical. They are canonically isomorphic. And our main example to keep in mind is the vector category with tensor product. Here, the identity object is the ground field K. If you take a tensor product with the field, you change nothing. And we have the twist map. A tensor B is not same with B tensor E, but they are really the same. So we call a functor or natural transformation monoidal if it respects the monoidal structure. Okay, so we will talk about cobordisms. What's a cobordism? You take two n-1 manifolds, sigma 0 and sigma 1. These should be closed. And the manifold M is a space-filling map from sigma 0 to sigma 1. We denote it like this. And this is n-dimensional. A very basic example would be an interval. We can think it as a cobordism from a point to point, just a straight line. And we put all this data into a category. This is called n-cob, and the objects are closed n-1 manifolds, and the morphisms are the diffeomorphism classes of these cobordisms. Some examples. I give examples in dimension 2 because it is impossible to visualize time at once. So we have U2. It is from the disjoint union of two circles to the empty set. The boundary of this part is the empty set. We have pair of paths from two circles to one circle. You read it from left to right. And we have birth and death cobordisms. It is from the empty set to the circle. And these have physical motivations, if you are curious about it. We will work with two cobordisms. And in this case, the skeleton, the essence of the category, is just given by the n many disjunction of circles. Thus, you take an object, it should be homeomorphic to one of these elements and the cobordisms between them. When we say two cobordism, we will mean this skeleton.
The previous slide, you had S1 bar.
Yes, because like if you go from here to here, the orientation reverses, but we will not use it much. Yes, yes. We have like two kinds. We have oriented cobordism category and unoriented cobordism category. So the first one is from oriented one. This is unoriented. So the distinction was important in the previous project, but this is just a recap. Okay, and here our monoidal operation is taking disjoint union and the usual twist map. With this, 2 cap is a symmetric monoidal category. Okay, so we have a functor theorem. The category 2 cap is generated by these 6 basic cobordisms. You can glue them. This is called the composition. The operation of the cobordism category is just gluing. And the disjoint union, you just put them together without gluing. And there are some obvious relations which are not important for us. Okay, so what's a TQFT? We can define it as a functor formally. It is a symmetric monoidal functor from the cobordism category with these operations to the vector category. And what is the intuition behind it? So it's an assignment. It maps closed manifolds to vector spaces and the cobordisms to linear maps between these vector spaces. And closed manifolds in physical sense are thought to be quantum states. And the cobordism, as I said, like space filling, you can think the direction as a time. And time evolution, it represents a time evolution. And in quantum theory, time evolution is given by unitary linear matrices. Okay, so we have a concept of Frobenius algebra. A K algebra is a vector space together with a multiplication. And the details of Frobenius algebra are not important for us, but it comes equipped with a structure. We have a bunch of maps, non-degenerate pairing, trace-like operation, multiplication, algebra multiplication, and the unit map. This structure is called the Frobenius algebra. And just forget about this and keep this in mind. The n by n real matrices form an algebra over R. The matrix multiplication is just our algebra multiplication. And the Frobenius homomorphism is an algebra homomorphism just compatible with the structure of these maps. Okay, so these 6 were the generators of our category 2 cap, and we can associate them with the Frobenius maps. So, for example, Frobenius form takes I said like it was a trace map, and it takes a matrix, produces scalar. Scalar is represented with the empty set here. For example, this represents multiplication. You take 2 matrices, and it produces you another matrix. We have this nice graphical calculus tool, and with the help of tool, we will prove our main theorem. I will just briefly talk about it. So, we want to put all this data again into a category, and TQFT category. The objects are symmetric monoidal functors, TQFTs, from n of the vector. In other words, this just represents the functor category, functors from n to vector, which are symmetric and monoidal. And remember that TQFTs are just functors, so our maps with the TQFTs are just natural transformations. So we represent it as an n TQFT. And here is our main, was our main theorem from the previous semester. So there is a canonical equivalence of categories in dimension 2. 2 QFTs are same with commutative Frobenius algebras. Yes.
Was there any restriction on the dimension of the vector spaces you get from this?
Yes. Like as a category, you take all vector spaces, but because of the Atiyah definition, they should be finite dimensional. Yes.
The informally calculate what is the result of dimension to result in
I don't know what. I just know it should be finite vectors, finite dimensional vector space, but I haven't seen an explicit TQFT. So, and in fact, we will see it in an extended case, which is very difficult to construct. So, knowing a dimension, like knowing the vector space, is very important in theory. Do you have a question?
C stand for
Commutative Frobenius algebras. And how do you prove this equivalence? You just like, this is basically generated by just circle. You just put n many circles, and if you send the circle to the A, basically you send n many circles to the n tensor product of A. And these maps, as we said, like for example, this is the identity map on cylinder. It just does nothing. And it is identity map on the algebra. And just by manipulation, you see that this gives a Frobenius algebra structure. So this was the TQFT case. And our aim in this project is to explain a similar classification result in the extended.
The image of identity becomes Frobenius algebra.
What?
So this is a functor, example of functor.
Yes.
And then we say image of one,
Mhm.
it becomes a commutative Frobenius algebra.
Yeah, together with these maps.
Mhm.
And algebra by itself, like, cannot be Frobenius algebra, it should be a structure, with these maps. And for example, if you glue a cobordism a cylinder, you change nothing topologically. It just enlarges it.
The dimension of A can be any.
Dimension can be but to finite dimension because of the non-degenerate pairing. This. But yeah, this was just the recap of our previous talk. Now we move to the main part, extended topological field theories. Again, it's an assignment. What does it do? It assigns n-2 closed manifolds a K algebra, n-1 dimensional cobordism a bimodule between K algebras, and n-dimensional cobordism between cobordisms, these cobordisms, it assigns to a bimodule homomorphism. And in a few slides, I will restate it again and put this into a categorical setting. It will be a bicategory. So before starting, like the first question that should come to mind would be, why do we need to extend it? TQFT is a nice theory. Why do we need to extend it? So, as I said, TQFTs are important for mathematicians to produce manifold invariants. How do we do it? Here, I draw an example. Let's take a two-dimensional TQFT set. So, we can take sphere as a cobordism from the empty set to empty set in one dimension. Now, let me change this. So, what does it do? It maps. It should be a map from Z of empty set to the Z of empty set. And this is symmetric monoidal functor. It should send identity monoidal object to the identity monoidal object. But in the weight tensor product, in terms of tensor product, the ground field is the identity. So this should be the ground field K, this should be ground field K, and the image of sphere is just a linear map between these two vector spaces. And a linear map is just determined by this image of the identity. So the image of sphere is just a scalar K. We associate K, the scalar, the Z of 1K, with the sphere and this an invariant. If something is homeomorphic to the sphere, they should produce the same scalar invariant. But the question is, how do we compute this map? This is you cannot just produce a linear map and then expect it to be compatible with other structures. So we do we divide the sphere into two. We see it as a gluing of two hemispheres. And what's a hemisphere? It is a cobordism from the empty manifold to the S1. And this is from S1 to the empty manifold. And the TQFT should respect the monoidal structure. So it sends gluing, which is the composition in the ANCOP category, to the composition of linear maps. So you reduce the problem into finding a linear map, a scalar, sorry, a linear map corresponding with this. But in this case, in dimension 2, this works nice. But if you go higher dimensions, or even, for example, you take a difficult object, then this is not enough. Just dividing into a codimension one is not enough, and you need to divide it into smaller pieces. But we cannot do it at that time because we have not associated, for example, in this case, a data to a point. We missed that. This is the reason we extend. And this is useful in two terms. First, as I said, calculating manifold invariant. And second, this approach is used by Troyev and Reshtekin in classification of three-dimensional TQFTs. So this is our motivation.
Give an example for any constitutional files for extended. Like it's like a rectangle.
We haven't defined eTFT yet. We will define in a few slides. So to define eTFT, we need the concept of bicategory. And this is where we come from. We will see. I will give an example of a two-covordism. Okay, so in order to define eTFTs, we need to extend our category. And in a normal category, if you take two objects, X and Y, the home set is just a set. If you want to see it as a category, this process is called enrichment. And at the end of this process, you get what is called a two category. It consists of objects, a class of objects again, and each object this time not only produces a set but a category, and the objects of this category are just morphisms between X and Y. These are called one morphisms, and the morphisms in this category are called two morphisms. So we will see examples soon. And in this type, for example, let me go here. We have X, Y, Z, and we have a bunch of maps between them. G and G prime. This is an ordinary description of a category, but with the two morphisms, we have vertical morphisms. For example, alpha and beta. Let's add these two. Let's say gamma. And this time you can compose these F and F prime, but also you can compose alpha and beta. You need another rule for composition. And not only that, let's say we have H and we have alpha prime, you can compose these two. And this is called here. And this is called a vertical composition. So composition of these two and these two are called horizontal composition, and the rule is given by a functor, not a ordinary map. And we have a concept of vertical composition. This is a general image inside the two category. And the canonical example you should have in mind is the category of categories, the category of small categories. Okay, so what comes to our mind when we say maps between maps? Just homotopies. What's a homotopy? Homotopy between two paths.
You also have associate.
Yes, we have.
See matching.
We don't have associated. Associated is just identity. In bicategory, we will have associators.
Oh, this is okay.
Yeah, this is
strict to
strict two category. Yes, we will also define informally bicategories. Okay, so on a topological space, you have paths, let's say alpha and beta, and the homotopy is just a continuous map. It takes alpha slowly to beta. It is the definition of homotopy, if you have seen it in topology course. And the composition of two paths is given by concatenation. So let's say you have a manifold on topological space. You have 2 points, A and B, and for example, alpha, beta. You go from alpha to beta, and then beta to alpha A to B, and B to C. And you can just see as a category whose composition is given by concatenation. Halfway through it, you go from A to B, and the other half time, you go from B to C. And the map is from unit interval to the end. So this is definition of concatenation. The formal definitions are not important. The point I want to make is that it is problematic. How? In this picture, these are homotopies between maps. What happens if we concatenate three maps? We have two ways of doing it. First, we can concatenate these two and then concatenate with the gamma, or we can just concatenate this and concatenate the result with the A. And if we apply the definition, we see that in the half time, we use gamma, but if you start with this, you only use gamma in the 1/4 time. So the resulting maps are not the same, but they are homotopy. This is the important thing to keep in mind. Concatenation is not associative, but the resulting things are not much different. They are isomorphic in our categorical sense. So the right setting for homotopy theory is not two-category because we don't have associativity. This is called the bicategory. And informally, you can think bicategory as a two-category whose associativity and unity laws are loosened. So you don't require something to be associative, but associative applies on it. The formal definition is just complicated with a bunch of diagrams, so I just gave the idea. And the first example, you can think any monadic category as a bicategory with just one object. You put the objects as endomorphisms of this object. And another important example is the bicategory of K-algebras. Here, objects are K-algebras. One morphisms are bimodules from between these two K-algebras. And the two morphisms are just bimodule homomorphisms. So this is the picture we have. Objects, one morphisms, and the vertical two morphisms. This category, bicategory, will be important for our purpose. Any question up to this point? Okay. So we will also expand our cobordism category into a cobordism bicategory. What do we do? Objects are, we go one dimension below. In the normal cobordism category, we assign data to just n dimension and n minus 1 dimension. In this case, we just go one dimension below, and objects are n minus 2 closed manifolds. One morphisms are just cobordisms between those, and two morphisms are n-dimensional cobordisms between these two cobordisms. It is very complicated, so here is an example of n equals 2. This is a two-dimensional cobordism. So you read it from right to, sorry, what is this? Right to left and top to bottom. Our objects are just points, and this object is just discerning of 2 points. And we have one cobordisms. So these are from 2 points to 2 points. You can go either just straightly, or you can just take discerningness of these two elbows. So these are our objects, one morphism, and the whole picture, which is a cobordism from W0 to W1, is a two cobordism. Is it clear? The description. Okay, so yes. It can be a manifold with boundaries.
We have two cobordisms which are combined between one.
Yes.
So in the definition, cobordism is structure that binds two closed manifolds.
Yes. Okay. So to define it formally, we need the concept of manifold with corner. So a manifold with corner is a manifold with a corner like this. So in a manifold with boundary, a boundary is something that is homeomorphic to the upper half plane. And in manifold with corner, you just take the positive axis. And for example, like in R3, this first what part? Fourth is the corner should be homeomorphic to this part. You see, this is just homeomorphic in dimension to the positive part of the true plane. So, okay, you need to also extend your definition of covariance from a closed manifold to a manifold with corner.
And here, this time your one morphisms are not up to
Yes.
They're actual.
Yes, we take actual.
Two morphisms are up to
Yes, I guess so. But yeah, I think so. Yes, you just loosen it. You just go one dimension higher and keep everything. Okay, so this is our covariance bicategory, and this time we have again a nice classification result by Schomer-Price. The oriented case has the following generators and the obvious topological relations between them. So the objects are points with the orientation, with the assignment of positive and negative. The orientation is not important. Just the unoriented case was a bit messy. I just wanted to show the oriented one. Generating morphisms are these two elbows with the opposite orientation, and we have these two, two covariances. So this is our classification. And now we can formally define an extended topological field theory. So let K be a field. It is a symmetric monoidal functor from the bicategory of covariance to the bicategory of K algebras. It is a functor again. And what does it do? It sends the points to K algebras. It sends one morphisms to the bimodules between K algebras. And this whole two covariance is sent to a bimodule homomorphism. This is just the way of saying this in a compact form. And indeed, the name extension deserves the name. So this definition extends our definition of an ordinary TQFT. If you just restrict yourself to the endomorphism category of empty cobordism, what you get is just, as you said, the closed ones. You just don't take the manifolds with boundary, and you are only left with. So this becomes the ordinary cobordism category, and this is just the vector space category. Okay, so this is indeed an extension of our original ordinary definition. Okay, how much time do I have? No power. Okay, good. Now we will start a difficult job. I will try to give a concrete construction. This is not very explicit, but this is the best I can do. And this time, like constructing an eTFT, if you can construct one, it means, I guess, writing an article on it. I couldn't find much examples that I can understand. So I changed the target category and I used the definition of Morton. And this time, the target category is not K algebra bicategory, but the Kopranov-Wodiewski two-vector space, which is an extension of the vector space category in another way. Don't ask me how it is done. Okay, so notation. This brackets means functor category. Objects are functors and the morphisms are natural transformations. This pi1 is the categorified version of the fundamental group of a topological space. And we see G, a finite group, as a category with one object. Group with called group with. Okay, what do? We will define an extended TFT, ZG, depends on G. So by this recipe, you can get infinitely many eTFTs. First, we define it on the values of manifolds without boundary. And then we will define it on covariances. And we will not use any dimension, so you can apply this recipe in any dimension. So we take an arbitrary manifold, and it is defined as a functor category between these two functors. So inside we have a functor category again, which is the category of functors from pi1b to the G, and you get this category and send functors to the vector space. This is very complicated definition. So let's see an example on B equals S1. So we need to make this thing explicit. And we know that pi1 of S1 is Z in your algebraic geometry topology. And we think Z, yes, and we think Z is a groupoid too, as a category.
But this has infinite many objects, this pi minus one.
Yes,
For each point in S1, you have a point. So you have like infinite
No.
Z's, right?
no, how do you do this? This is just pi1 S1. Normal pi1.
Yeah, so you said
Yes, and this is just Z.
so how many objects does pi one S1 have?
It's one object. This is just the group weight with one object. So a category with a point and the that are just endomorphisms. But indeed, we do it for any category.
For well, for the fundamental group, you don't have to choose a point. It's
No,
not
no.
defined for pointed spaces. It's defined for all spaces.
Yes, but okay, first we have this, and we see any group in a categorical setting, which is a category with one object, and the elements of groups are just embedded as maps. So in this case, the big pi1 is just a categorification of the usual fundamental group with one object, and the homotopy loop groups are just morphisms on this arbitrary point. This point is not from S1.
Up to categorical equivalence, you're right. But actually, as a category, this has infinite many objects. And each path gives an isomorphism between the objects. Like if you have a path connected space, each object will have isomorphic automorphisms. Automorphism.
So you said like, you also see pi1, normal pi1 as infinite many objects.
No. I mean,
So what is the problem with categorification?
you said default.
Yes.
So you're saying you're considering fundamental group as a category.
Yes.
Okay.
So the group point definition is wrong?
Yes, that's not the default.
Okay. Okay, thank you for pointing this out. So it is a category with one object whose elements are loop spaces.
Category very good.
So we will take the basic one, the easy one. Okay, so we just think this as Z, and this is functor category, functors from Z to G. So a functor is determined by its image on the morphism 1. We see 1 as a morphism by the additive structure of Z. A functor is determined by its image on 1. So if 1 is sent to a G, an element of group, so we know the functor. So functors are just equivalent with group elements, and the natural transformations between them is just given by another element H in G, and by drawing some diagrams on the between categories, we get by nature of the condition GH equals HG prime. So it's just conjugation action. Okay, so we can think this as a category whose objects are elements of G and whose morphisms is the set H such that GH equals HG prime. Okay. So we will not go that much explicit. And again, so we call this as C, category C. And this is just the functor category of C comma vector spaces. And these objects, its objects are the functors taking the G and assigning to a vector space. And the morphisms, it just sends H to a linear map, which is compatible with this conjugation operation. This is as explicit as I can get. So it is not much concrete, but at least you have a recipe. And if you reduce it further, using the tools of algebra, you get a definition. By choosing a G, you get a TFT. So far, we have only defined it on manifolds without boundary. Or we didn't say without boundary, but just arbitrary manifold. What happens on cobordisms? So we want to define its value on M. It's a manifold from B1 to B2. So ZG on cobordisms. We write it as a cosphere diagram. These are just in boundary and out boundary, and these are inclusion maps. And you apply taking fundamental group weight operation, and you end up in a diagram in the category of categories. So these are all now categories. And we still have inclusion maps. I call them the same I.
So for example, we will be difficult. Because like the point we select will be one may not the point we select.
So what
I mean, B1 and B2 are like on separate parts, but they go to different points. So how do you map that into which point you select now?
okay, how do we see pi1 as a category with one object?
So it's just points in M are objects,
Points in M are
and cats between them are morphisms of the homotopy. Like
okay.
the homotopy classes of cats between.
So you also then you also see this as a okay. Let's take does it work? Like sample point in
Like
plus one.
objects are points in M, like pi1 M. Objects are all points in M. Objects are M.
Okay, if we then what happens if we take the point S1? Like let's just specify this point, and our like interest is just group space on this
Okay,
particular
but
point.
that's not every point is an object.
We don't want this.
But
But
this,
do we want this here?
yes, you want.
Okay. Okay.
Because if you choose a point in M, how do you map to that point from B1 and B2 at the same time? I mean, okay, fundamental group weight of M is by definition a category whose objects are all points in M. And morphisms are paths between these points up down. So if you choose just one point, it's just the fundamental.
Okay. I didn't know that.
And
General
if M is path connected, then all the fundamental groups are isomorphic to each other. So up to categorical equivalence is just one fundamental group.
Okay. So in this case, we can't take a distinguish.
You can't just work with fundamental group. You really have to work with the fundamental group.
Okay. Okay, so we take the fundamental viewpoint, and inclusion maps are just inclusion factors in that case. And we again apply another factor, which is contravariant, this one. And you see the arrows are reversed in that case, where the pi is defined to be the pullback of the inclusion map. Again, we apply another contravariant factor to get what we want. And in this case, so we apply two contravariant factors, and the arrows are in this direction now.
And also, saying that how we call is it like something like projection?
You just, I guess, take a point, like it's an inclusion. It's sends the boundary, it maps boundary to the manifold, and what the pullback is just defined on the boundary. Other parts, pi one, I guess is not defined.
And also, it is why do you need to consider functors between fundamentally and
Functors between this.
Is this notation stands for
Presentation about
log that?
This
no about answers.
this
Yeah, this is
is a functor.
Yeah,
Yeah.
or no, all the functors from dash to
No. This is just the. I leave that part empty. It's like the home function. We leave that part empty, and you, for example, there's
so all functors.
yeah. This
I'm sorry, but why do you
object among for increasing.
Okay, so we have this diagram, and what we want. Remember that these are just Z G B1 and this is Z G B2. And we want to map from this to here. In this diagram, we don't do it. But what we have is, what we know is, I don't know, but the book knows, this pi 2 star is an adjoint. I don't know how we get this. And we can define this, first go from here to the above, and then come back here with the adjoint. Now, taking the composition of these maps, we send our cobordism to this, I guess it is part.
It's natural. It's not committed. It's natural. We don't want this not commute here when you take this map with Zatra. We say you're taking by one star with the adjoint, right?
Yes.
This is the adjoint, so it's really like as a triangle. What is the bit? It's a natural zone. Yeah, okay.
It's just I just take the adjoint and compose it. Just I guess these are functors, and but we are in the category of categories, I guess, and we just take the composition in the functorial sense in our bigger category. Okay, so we have the definition. So as you see, the constructing an example is very difficult. I don't understand what the steps here, but I just wanted to give an idea on how these are constructed in this. Okay, so we come to the last step in our presentation. Again, we have a classification theorem by Schomer-Price. The bicategory of two-dimensional oriented extended topological field theories with values in algebraic bicategory of K algebras. So this category is equivalent to the bicategory of Frobenius algebras, which we define now. So in this category, in this Frob category, the objects are separable symmetric Frobenius algebras. I don't know what separable means, but we need that in the classification. And our morphisms between Frobenius algebras are compatible Morita contexts, and two morphisms are Morita context isomorphism. So what's a Morita context in this case? We have two K algebras, A and B. Normally, an equivalence in the category of bicategory of K algebras is isomorphism. If they are isomorphic, they are certainly equal. But this is too strict in our case. And we define another equivalence, Morita equivalence. If you have the Morita equivalence is defined by this four data, these two bimodules and these two bimodule isomorphisms. So if you can go from A to B with the bimodule B and A, and then compose it with, like composition is given by tensor products in this category, then you get a map from A to itself. You get a bimodule over A, left and right A bimodule. If it is isomorphic to the identity, which is this, then, and it also happens for B. If you go from here and come back, you should get B left and right, B bimodule, then we say that A and B are equivalent. They are called Morita equivalent, and this data of 4 things is called a Morita quantums. So the theorem is very hard to understand, and the proof is a PhD thesis of 300 pages. I had no idea how they proved it. But at least I can give some remarks on the classification. So we have a famous hypothesis called cobordism hypothesis by Baz and Dolan. It was hypothesized by these guys and proved by Lurie in 2009. It says that basically, in a simplified way, an extended topological field theory is determined only by its value on a point. So in our case, in dimension 2, a point is sent to a K algebra. So a K algebra determines all eTFT. And normally, as I said, the equivalence of algebras are algebra isomorphisms, but this is too strict for our case. This says that this cobordism hypothesis combined with the result of Schomer-Price says that if two eTFTs are equivalent, then they are equivalent on the point. And this is by cobordism hypothesis. And equivalent on the point means that equivalence of algebras, because a point is sent to a K algebra. And in the category of Frobenius algebras, equivalence is given by Morita equivalence. So if you had taken it to be an isomorphism, algebra isomorphism, we couldn't have the correct notion of equivalence of eTFTs. That's why we take Morita equivalence as equivalence instead of the strict one, the isomorphism. Okay, so
for eTFTs, we just 2 dimensions.
no, it is defined in general. It is defined very generally. Yes. So it is n-dimensional.
But what does a point mean? Like point is 0.
In our case, this is the remarks on the classification theorem, which is valid only in dimension 2.
Okay, so this time we are restricting to that.
Yes, yes.
In the last thing you're restricting to dimension.
Yes, yes. In the cobordism, you mean cobordism hypothesis?
No, the last slide.
This?
Something. Yes. Like 2 also.
Yeah. This is in dimension 2.
That's in dimension.
Yeah. Because I combined the classification theorem, which is valid for dimension 2, with the cobordism hypothesis in dimension 2. This is, in general, the statement is that an eTFT is determined by its value on a fully dualizable object. And in our case, it corresponds to a Frobenius separable commutative Frobenius algebra. Okay. So in summary, what have we done? In the first part, I talked about TQFTs, and we dealt with the dimension 2. And in dimension 2, cobordism has a nice representation with its generators. And a TQFT is an assignment of physical phenomena to algebraic phenomena, because we understand algebra better. We can work on Frobenius algebras, but working on TQFTs is difficult, as you see. And in dimension 2, we have classification theorem by means of commutative Frobenius algebras. So this is not only equivalence of TQFTs with Frobenius algebra, but to TQFT as a category. Those objects are TQFTs, and morphisms are natural transformations. Is equivalent to this category. And objects are commutative Frobenius algebras, but we have also Frobenius homomorphisms. So a categorical point of view, gains are more implied than just set theory. This is our motivation for using categorical theory. So in the second part, we talked about extended topological field theories. I mentioned why we need an extension. We have a motivation of producing knot and manifold invariants. And to define its extended topological field theory formally, we need to extend category theory. First, we extended it into 2 categories. Then we saw that, by the example of holotopy theory, this is not enough. We loosened some laws a bit, and we got a bicategory. And you'll see that in dimension 2, this bicategory of cobordisms still has a nice representation. So we are not here. And in dimension 2 again, the classification is given by some form of Frobenius algebra.